Hello and welcome to this video on growth curve modeling in the structural equation modeling versus multi-level analysis frameworks. My name is Geiser. I'm an instructor with QuantFish. Many people don't even know this, but latent growth curve models can be specified as either structural equation models or, more specifically, confirmatory factor analysis models, or as multi-level or hierarchical linear models. And so in this video here, I want to talk about the different specifications within SEM versus ML. I also want to show you the different data structures or what the data has to look like for an analysis in either the SEM or ML frameworks. I will show you an example of how to specify a growth curve model in the SEM framework and the multi-level framework using the Mplus software, which happens to be one software in which you can go either way, SEM or multi-level. And then finally, I want to discuss the pros and cons of using one framework over the other for specifying latent growth curve models. So let's get started and let's talk about the specification first, starting with a growth curve model in the structural equation modeling framework. Here I have a simple growth curve model that assumes linear growth. And in this model, I have 4 time points in this example that are represented by observed variables y1 through y4 in boxes below. And in this model, there are 3 types of latent variables. We have an intercept factor that represents the true scores at the onset on the first measurement occasion. We have a slope factor here that represents linear changes over time, and we have measurement error variables epsilon for each time point. This is a linear growth curve model because the intercept factor has all loadings fixed at 1 and the slope factor has loadings fixed to the rate of change or the time points here 1, 2, 3 in this way. So say the second time point is fixed to 1, the third time point has a loading fixed to 2, the fourth time point has a loading fixed to 3, and so that makes the slope factor a linear change factor representing linear growth or decline across time. You can see that this model implies a special type of confirmatory factor analysis where certain variables have loadings on both factors and where we have all loadings fixed a priori. None of these loadings here are estimated, although in other types of growth curve models we can leave certain loadings on the slope factor to be freely estimated if we want to estimate the shape of growth from the data. And so this model can be specified as a measurement model or confirmatory factor analysis model in software programs that can handle structural equation modeling or confirmatory factor analysis such as Mplus, LAVAAN, and other programs. The model can also be described with a single measurement equation for a variable y at time t. So the observed variable yt depends on the intercept factor, and then t minus 1 times the slope factor. T minus 1 indicates the fixed slope factor loading plus an epsilon error term that is specific to time t. Now, what does the data structure need to look like in order to fit a growth curve model using the SEM/CFA framework? For that, we need to have our longitudinal data in wide format. Wide format means that for each time point for our variable, we have a separate column. So in this case, where we have 4 time points, we have 4 columns in our data set, where each column represents the scores on the outcome variable yt at a given time point. So y1, y2, y3, and y4 reflect the scores on the same variable at 4 different time points. And it's called a wide format data set because it becomes wider and wider and wider if you have more and more and more time points. For each time point, there's an additional column. And this is opposed to long format data that, as we will see later, has to be used when we specify growth curve models within the multi-level modeling framework. Here's an example of how to specify a linear growth curve model in the Mplus software, which is a program for structural equation modeling and factor analysis, but also for multi-level analysis. And so in Mplus, we can set up a latent growth curve model within the SEM framework very easily with just a few lines of code. You can see I have a title command here, which is optional. I have a data command that lets Mplus know my data file, here named growth.dat, which contains those wide format variables that I just showed you. The variable command labels those as y1 through y4, and then the model statement consists of just a single line of code that is given by the special Mplus syntax for growth curve models. Intercept is the intercept factor, slope is the slope factor. Those are labels that I picked. And then behind the vertical bar here, the symbol, we have the 4 variables with loadings fixed according to linear growth on the slope factor. The first variable doesn't load on the slope factor, so has a loading fixed at 0. And then y2 has a loading of 1 on the slope factor, y3 has a loading of 2, and y4 has a loading of 3. The output line allows us to request sample statistics as well as the standardized solution STD-YX, so that we can also take a look at the correlation between the intercept and slope factor. So Mplus has very straightforward syntax for specifying a growth curve model within the multi-level modeling framework, and this is still very straightforward also if you have a quadratic growth curve model or some other kind of growth curve model. All the relevant parameter estimates, such as the slope factor mean and variance, the covariance between intercept and slope, and the error variances are estimated by default, so you don't have to specifically list those in the Mplus syntax. Next, let's talk about the specification of a linear growth curve model within the multi-level modeling framework. And we'll see that that is slightly more complicated because we have to specify a model at 2 levels. So at level 1, we have a random coefficient regression model where our outcome variable y is regressed on time using a random coefficient regression equation with a random intercept beta 0 and a random slope beta 1. And so this is shown here with these black dots in the notation that Mplus uses in their user's guide to depict random intercept and random slope models. The dot on the arrow from the predictor time to y indicates that the regression of y on time has a random slope, and that random slope, as we will see later, represents the latent slope factor, the linear slope factor in our growth curve model. Furthermore, this regression of y on time also comes with a random intercept beta 0, and that represents our latent intercept factor in the growth curve model. And there's an error term epsilon that represents measurement error. At level 1, the model can be expressed by a random coefficient regression equation that you can see here. So y for individual at time t is equal to the intercept term for that individual, beta 0i. So everybody can have a different intercept score, and then plus beta 1i times the time predictor variable, where both the slope can be individual specific and also the time point can be individual specific. And then we have also an error term, which here I indicated with RIT. So that's actually epsilon. So I forgot to change that here from RIT to epsilon. And then the level 2 model consists of the random intercept beta 0 and the random slope beta 1, which are latent variables in the Mplus framework. And so for those two latent variables, we estimate their mean, variance, and covariance. So there are 2 level 2 equations, one for the intercept beta 0 and one for the slope beta 1. And so both are broken down into a mean, gamma, and a deviation from the mean, u. And so for u, we can estimate the variance, and then that's the intercept and slope variance, as well as there's a covariance that is indicated here by the double-headed arrow. Now, this latent growth curve model is equivalent to a model that can be specified within the SEM framework if we assume that the measurement error variances, so the variances for epsilon, are held equal across time. So you'll get exactly the same parameter estimates for this model when it's estimated within the ML framework as you would for an SEM specification of the same model. So those models are equivalent. However, this one here can be specified within or as a multi-level model or random coefficient regression model. Now, what does the data format look like for a multi-level specification? This is now long format data, and here you can see that we need only 3 variables as opposed to 4 that we needed previously in the wide format data structure. Here we have only 1 column for the outcome variable y, and so therefore, because there's only 1 column, we need to indicate the time, and so we have a time variable. That's the second column here that indicates the measurement occasion. You can see here the first one is time 0, then we have time 1, then we have time 2, then we have time 3. So the 0 through 3 represent the 4 time points on our time variable. And we also have a person ID variable that shows us to which person each of these scores belongs. And so you can see the first 4 rows here belong to the first person. So they reflect the 4 scores that were measured for person 1 at time 1 at different measurement occasions. So across those 4 time points, those are all scores from person 1, and then next we have person 2 with 4 time points, then we have person 3 with 4 time points, and so on. You can see for person 5 we have only 3 time points, and that's not a problem when we analyze data in this way, because the multi-level modeling framework can readily accommodate different numbers of time points per individual. Also, the time doesn't have to be discrete like this. The time could be in minutes, the time could be more precisely measured, there could be varying time intervals between persons, within persons. So there's a lot of flexibility with regard to this time variable when we specify a model within the multi-level modeling framework. Now, this is called a long format data structure because obviously when you stack those 4 columns for the 4 time points into one column like I did here, then the data set becomes a lot longer but is not as wide. And so that's why we call this a long format data structure. As an aside, it's very easy to restructure wide format data into long format data and vice versa. For example, Mplus has specific commands like, for example, a wide to long command where you can transfer or transform wide format data to long format data very easily. So if you want to switch between these different specifications and you have your data structure in one structure or the other, you can easily reconfigure the data for either type of analysis in Mplus, and other programs do that as well. Now here's the Mplus syntax for a growth curve model specified as a multi-level model. You can see that this is a little bit more complicated. We need more commands for that. Specifically in the variable command, we not only need our names command, but also we need a use variables command so that we can pick the relevant variables from our names list. So in the model, we will only use the outcome variable y as well as time. We won't use the ID variable. Therefore, we need to have a use var command. And then also we need a within command here to specify which variable acts as a level 1 predictor, in this case our time variable. And then we also need a cluster variable specification to allow Mplus to figure out how our 2-level structure here is defined, or based on which variable we define level 1 versus level 2. In this case, that's the person ID variable. Next, we have to specify analysis type equals 2-level random, because this is a 2-level model with a random slope. And so we have to tell Mplus that that's the case. And then in the model statement, we have both a level 1 model, that's the within model in Mplus. So within persons, we have our level 1 model, and then between we have the model that's between individuals. at level 2. And so within consists of a command that specifies a random slope in the regression of y on time using this command slope y on time. And then at the between level, we only have to specify that the random slope from level 1 is allowed to correlate with the random intercept. And so that allows for the covariance between the intercept and slope factors. The other parameters are estimated by default. At level 1, we will get the error variance var epsilon, and at level 2, we'll get the intercept factor means, or the intercept and slope factor means, variances, and the covariance automatically. The output line here only has the sample statistics command because a standardized solution in Mplus requires a special estimator within the multi-level modeling framework. So you'd have to choose a Bayesian estimation method in Mplus in order to obtain a standardized solution. And that's perhaps an advantage of the SEM specification, that we can get the standardized solution without having to resort to a special type of estimator. Now let's talk about the pros and cons of the SEM versus ML frameworks for specifying latent growth curve models. And I'm going to begin with the SEM framework and talk about the pros of that approach, and then we'll later see what the cons are of the SEM approach when I talk about the pros of the multi-level approach. So first of all, one advantage of the SEM approach is that when you already know it, when you already know how to do confirmatory factor analysis and structural equation modeling, but you maybe are not so familiar with multi-level data analysis, then it's easier to do a growth curve model as an SEM model than it is to learn multi-level analysis. And so that would be one advantage, that if you already know that SEM framework, it's very easy to apply growth curve models. Also, within the SEM framework, we have the advantage that we can test a growth curve model more rigorously. There are more fit statistics available when we test a growth curve model as a confirmatory factor analysis model than when we test it as a random coefficient multi-level model. For example, we get a chi-square test of model fit within the CFA framework, which we do not get when we specify the same model within the random coefficient regression framework. Also, there are other fit statistics such as RMSEA, SRMR, CFI, TLI, and so that's clearly an advantage of the SEM framework, that there are more statistics, more fit indices related to absolute model fit than we would get in the multi-level modeling framework. The SEM framework is also more flexible in terms of handling different error structures, such as freely estimated error variances across time, autoregressive structures, correlations between error terms, and other types of error structures. The ML framework makes it a little more difficult to, for example, estimate error variances freely across time. By default, they would be held equal, which may not be realistic. And as we saw previously, standardized parameter estimates are harder to obtain within the multi-level modeling framework than they are within the SEM framework, where they are readily available for estimation in Mplus. We use stdyx to get the standardized solution, and other SEM programs also would make it really easy for you to get standardized parameter estimates, which are not so easily obtained in some multi-level analysis programs. Also, when you have more complex growth curve models, for example, ones with multiple indicators at each time point, such as second order growth curve models or multiple indicator growth curve models, then the specification is much easier within the SEM framework and also more flexible. If you were to use the multi-level modeling framework to estimate multiple indicator growth curve models, which is possible, then you would have to apply multi-level SEM, which is more complicated and not supported by very many programs to date. Mplus would allow you to do that, but other programs for multi-level analysis may not allow for multiple outcome variables in that way. And then finally, when you have multiple indicator growth curve models, you want to test measurement equivalence across time, and that is something that is more easily done within the SEM framework than within the multi-level modeling framework. Now let's talk about the pros of multi-level modeling for growth curve models. And so again, if you are somebody who is more familiar with the multi-level modeling framework than the SEM framework, then it would be easy for you to do because you already know how to run a random coefficient regression analysis, but maybe you don't know how to run a confirmatory factor analysis, and then it's maybe easier for you to apply those models within a framework that is familiar to you. Also, when you use the multi-level modeling framework, you don't have to buy SEM software or learn SEM software. It can be done in many common programs. Even SPSS supports multi-level modeling. And so any program that supports multi-level regression analysis could be used to estimate growth curve models in long format or with long format data. And so then you wouldn't have to learn or apply structural equation modeling software if you're not familiar with that. And then another advantage of multi-level analysis is that it can easily handle many time points. So if you have 10 time points, then it can become tedious to specify a growth curve model as an SEM, whereas there's no additional trouble when you specify it as an ML model because the multi-level long format data structure doesn't care how many time points an individual has. Maybe somebody has 15 time points, and that doesn't make the model more complicated to specify. It's the same random coefficient regression model no matter how many time points you analyze. And in the same vein, it's also easier in the multi-level modeling framework to handle unequal spacing of time between and also within individuals. So individuals may vary widely in terms of when their scores were recorded, and they may not have been recorded with the same time intervals, and then that can be complicated in the CFA SEM framework to take that into account. Then you'd have to use t-scores and other adjustments, and it could be complicated, especially if the time points are unequally spaced for different individuals. When there's variation between individuals in terms of when the measurements happened and there's imbalance, then the multi-level modeling framework has advantages because it can easily accommodate that through the time variable, which is flexible. Also, the multi-level modeling framework makes it easy to handle missing data in terms of missing time points. So if somebody has only 2 time points as opposed to 4, it doesn't matter. Even if somebody contributes only 1 time point, that person can still be absorbed into the long format data set and can be part of the estimation, can at least contribute information regarding the intercept factor and the first time point, and so that's not a problem and is readily accommodated in the multi-level modeling framework, whereas when you have missing data in the confirmatory factor analysis framework, then you'd have to think about how to address that either with full information maximum likelihood estimation or with multiple imputation. And then the question becomes whether the software program that you're using for SEM offers that. Now, most SEM programs do offer full information maximum likelihood. Some even offer multiple imputation. Mplus is one of them that offers both FIML and multiple imputation. So it's not the biggest problem. However, it is somewhat more easily addressed within the multi-level modeling framework. So overall, you can see that they have both pros and cons. Overall, I think I would slightly favor the structural equation modeling framework because of the fit statistics that I would get as long as I don't have too many time points and as long as the time points are not imbalanced too much. It seems then more straightforward to apply the SEM framework. If you have many time points and or unequal spacing between time points, then the multi-level modeling framework may be the better choice. I hope you found this video useful to learn more about structural equation modeling versus multi-level modeling of growth data. If you did, please subscribe to this channel. Don't forget to check out the description for additional resources, including workshops on growth curve and other longitudinal models that we offer through QuantFish, and I'll see you next time.